Now that you understand how k-means models work, let's look at a slightly more complicated example involving what's known as Gaussians. So let's understand why we want to use this new model over k-means. So what are the limitations of using k-means clustering? First of all, k-means is a hard clustering model due to the process it uses. The idea that we're finding averages of data points that are parts of groups means that we can't afford to have probabilities of groups or things like that when calculating the mean for the new centroid. So that's why it's a hard clustering algorithm. And as well as that, it only plots areas in a radial fashion. For example, on the 2D example, it's a circle area that it plots. On the 3D example, it would be a sphere. This can restrict how the model classifies and groups different data points. Taking the example on the bottom left, we can see this in action. So clearly there are two categories specified by lines and colors in the blue and the red. On the right, we have a k-means model trying to classify the data. However, it fails because it can only plot circular regions, and due to the line nature of this data, k-means doesn't stand a chance of classifying it. So how could we use Gaussian mixture modeling to solve this problem? Well, before we get into that, we first have to understand what Gaussians actually are. So Gaussians are functions in mathematics that can be used to represent what is known as probability density. Gaussians are a probability density function. Now, to understand what that means, you have to understand what probability density means. So a probability density or probability density function essentially tells you what the probability of something happening is given an event. So let's take the example of height. Let's pretend this is the probability density function of height around the world. So near the middle, you might see something like 1.6 or 1.7 meters tall for an average human. And on the y-axis, you'd see the probability of being that specific height. Now, the total area should sum up to 1 ideally, so the probability of being any height is 1, right? Because everyone is a certain height. Now, what if I were to ask you the question, what is the probability of someone being 1.7 meters tall? So you might be inclined to just read off the y-axis and say, oh, well, we just stick p 1.7 in, and that would give us the probability of being that height. Now, unfortunately, that's wrong. The idea is that height is a continuous variable. As explained in linear regression, there are several infinite. There's an infinite continuous line of heights. So someone can be 1.7 meters tall, and someone else could be 1.701 meters tall, and someone else could be 1.7001 meters tall. There's an infinite range. Therefore, the chance of being 1.7 meters tall to the exact atom will be incredibly improbable. This improbability is represented by the width of the line. The actual probability of being 1.7 meters tall would be the width of the line times by the height. The area represented by the black line would be that probability. In real life, this would be much more thin. Now, if I were to ask you what is the probability of someone being around 1.7 meters tall, we could do the following. We could say, okay, 1.7 meters plus or minus 0.05 meters. Now we have an area that's more workable. We have an area to find over a given curve. Of course, you need to know integration to find the actual area, since integration is used with curves to find areas, but this is the general idea. There are an infinite amount of small points, but when we take a range of points, it's much more easier to understand the probability of something happening. So that's the idea behind probability distribution. You can use this idea of probability with certain data points and distances from clusters to give you the probability of a certain data point being a member of a certain class. Gaussians are specifically probability curves which are defined by this function. You don't need to understand why this function works, but rather just the idea of it being implemented behind the scenes. So we have our specific probability density function, and it nicely integrates to give us a nice way to find out the area represented underneath a curve, which in turn will tell us the probability of a certain data point being a member of a certain class or group. When you apply this and visualize it, you'll get something a bit more like this. Because of the way we can stylize the Gaussian function, we can create more complex shapes like ovals, and we'll achieve this soft clustering type effect where the probability is distributed nicely. As a result, we'll be able to group these larger, longer lines where k-means failed. This process is also known as mixture modeling, or this general idea. So Gaussians allow us to cluster somewhat intermingled data, or data that wouldn't normally be predicted by k-means. Alongside this, there's another popular clustering method called dbScan, and it's a rather primitive method, but it's very effective. It's essentially like spreading a cluster between multiple data points. So if data point A is part of group A, and there is another data point close enough to it, it will also become part of group A. It's a very, very simple algorithm to understand, and I go into more depth with it on the notebook. And it's a very fast and intuitive algorithm, and has quite an effective outcome. So that's more into the Jupyter Notebook that you can go after this. But just to recap over the sessions, over this session, what have we covered? So we've covered the uses of clustering in the real world, including pre-processing data for supervised learning, pattern recognition, data reduction, all used for academic, sciencey, or maybe even economics, financial fields. We've covered specifically hierarchical clustering used in biology, mainly with genetics. We talked about k-means clustering, which can be used in economics and finance, and Gaussian mixture modeling, which is just an extension of k-means clustering. And we'll also go over dbScan in the notebook. So hopefully the way I've presented the Jupyter Notebooks using the frameworks like sklearn and going into more depth behind the scenes, you should be able to create and produce your own clustering algorithms in whatever medium you'd like. And hopefully this has inspired you to use some of these algorithms in some of your own AI projects. So with that, I'd like to say thank you. My GitHub is jrahala in case you need some more resources. And do feel free to contact me through Discord or any other means, and I'll be there to be able to offer you a helping hand. Thank you for listening. I've been Jazamrit Rahala. Thank you.